Hello, friends. It's Ben again. This is another of my riveting series of videos for vector calculus. I know you're super excited, and I'm going to blow your mind when I talk to you about Stokes' theorem, right? As I referred to in class, I think it was today, Stokes' theorem and Green's theorem really are very much related to each other. Stokes' theorem is essentially the version of Green's theorem that exists in 3 dimensions. Whereas Green's theorem had the m in p, oh, I'm sorry, the m and n for the function, and the area integral that you were looking at was an integral of n sub x minus m sub y. If you labeled them something different, then you have to figure out what I mean. But whereas you've got that for a double integral, now with Stokes' theorem, instead of that, you will be talking about a surface integral of the curl of your function f, which will have an m and an n and probably a p for the third entry in it. So you have this surface integral of the curl of f being equal to this line integral, the line integral being around the boundary of the surface itself, positively oriented. Positively oriented, again, means that you have to think about where you are on the surface and that you are having the upright direction be the direction of your normal vector. So you know how it always said oriented upward or oriented inward or something like that. So you have to think about that as the up, and then a person who's walking along the boundary with that up, then their left-hand side should always be toward the surface and their right-hand side should be off of the surface, and they walk along that boundary. Now, if you have a surface with holes in it, then you've got to think about one side is going to be going clockwise and one side's going to go counterclockwise. And it's very much a visualization sort of thing. So let's go ahead and see the statement of it here. And I will share screen and hope that everything goes well with the sharing of the screen. So screen mirror, 3, go. Okay, it paused longer than I thought it was going to. Scared me there. All right, so here we're taking a look at Stokes' theorem. And we're saying that this integral around the boundary that is oriented positively is equal to the surface integral of the curl of f, and this ds vector will have an orientation which is upward. Let me see whether I can do this here. I'm going to grab my n vector. Yes, I can. So if we are walking along that boundary there, with that being our upward direction, then we have the direction we're walking being forward with that orientation, and to the left is the surface. All right. And maybe I should not leave it quite like that. Maybe more like this. Okay. So now there is one caution there. I've not written out the entirety of Stokes' theorem. You should go look it up and make sure, because we looked at an example today on Green's theorem where it looked like Green's theorem applied, but it didn't. If you have some sort of discontinuity in your vector field, you can't apply Stokes' theorem. And worse even than that, because of the fact we have curl of f, and curl is a derivative operator. That means that we not only can't have discontinuities, we can't have discontinuities in the derivative, okay? I suppose technically there's a question of how discontinuous, but anyway. So then terminology stuff, there is this term that gets used in some of the problems that so far as I could see wasn't defined anywhere in the text. And then I found it mentioned just in passing in the summary at the end. And that is that when you talk about the circulation around the boundary, what that's talking about is doing the line integral, okay? So this would be referred to as calculating the circulation around the boundary. All right, so all of these problems here, I'm not working them out on the fly because I started to record that video and I just kept making arithmetic mistakes and I had to erase it and start over. So this is all worked out ahead of time, so it should all work out, but it also lacks some character because you don't get to see how I thought through it and all that sort of stuff, okay? So these questions where it says to verify Stokes's theorem, often it will say to verify that Stokes's theorem by direct calculation or something like that. But we're verifying Stokes's theorem for a surface S being the portion of this plane that's in the first octant and the vector field given by yz comma 0 comma x, right? So just a super brief sketch here. Not trying to get it to scale or anything, but the place that we hit the z-axis there is going to have the coordinates 0, 0, 1. The x-axis will be 2, 0, 0, and the y-axis will be 0, 0, or 0, 3, 0. Okay. Weirdly, it looks like that 1, 2, 3 was there for a reason, and it totally wasn't. Okay. All right, so let's do the surface integral part of it first. And so I have to parameterize it. It being a plane, it's super easy to parameterize. And so I'll just say x and y and 1 minus x over 2 minus y over 3, okay? And then with that, because we have to stay there in the first octant, we'll have our x values go from 0 to 2. So that's, going along the x-axis here. And then our y values are going to have this cutoff here. And the way that I figured that out was to set the z equal to 0 and then solve for the y. Okay. So that's the setup there. Please bear in mind that because of the way this is cut off, we could see it's a triangle. So it's going to set up something like that. Now, you don't have to have parameterized it in exactly that way. It would totally make sense to pick a point, say this 2, 0, 0, and this vector here and this vector here, and then take t times that vector, and then s times that other vector, and then do something with, say, t going from 0 to 1 and s going from 0 to 1 minus t. Okay, that would be a perfectly valid way to go at that as well as the way that I wrote it down here. Okay, but if you write it down this way, you'll take your g sub x and your g sub y, and you'll take their cross product, and the cross product I get would be the normal vector to the plane written precisely as you're seeing there. And that's something from Calc 3 that you might remember pulling out the normal vector to a plane. So, all right. So once we've got our normal vector there, we've got to think about what the curl of the vector field is. And so I just lay out, because basically the curl means to take the gradient operator and cross it with your vector field. So I just lay out my ijk and my partials and then the vector field itself. And then I go partial of x with respect to y is 0, and 0 with respect to z is 0, and I get 0. and then partial of yz with respect to z is y, and the partial of x with respect to x is 1, so I get y minus 1. And then the partial of 0 with respect to x is 0, and the partial of yz with respect to z is, or with respect to y is z, and so I get a negative z because that was the second one there, okay? So this is the curl, and so I take the curl and I dot it with the normal vector, and I get this y minus 1 over 3 and then minus z. And I'm integrating, remember that we said it was 0 to 2, and then 0 to 3 minus 3 halves x, okay? So once you have the integration set up there, it's just going through and simplifying. We did have to see that since z appeared in there, we had to go look and see what the z was in this. If you had a fancier parameterization, then you might have to go look up all three of them. So anyway, once we've got the quantity there that we need to integrate, we integrate with respect to y first and plug in the limits. And when we do that, it looks horrible. But then we do some algebra there, and then we do some more algebra, and we notice that we have 3/4 x squared minus 3/4 x squared, which makes it a little bit less miserable. And that all simplifies down to minus 1 plus 1/2 x. And so you're integrating that with respect to x from 0 to 2. So minus x plus 1/4 x squared, 0 to 2. And then you just plug in the 2, and then the minus the 0 part just gets you 0. And so we end up with -1 out of it. So we expect to get -1 out of doing the line integral across these three segments and adding them up, okay? So what I did here was to split those up, and when x is equal to 0, that means that we are in this plane here, but we don't need anything other than just that line segment there. So parameterizing that, since we are, hang on, I may be looking at the wrong thing there. Yeah, since we are, what in the hell? I'm sorry, folks. I'm getting mixed up about where I'm at on this. So we start at 300, and we want to go to 001. Okay, so apparently we're going this direction on it. I thought we were going the other way. Okay. Well, yeah. So apologies about that. I have, in fact, parameterized this backwards, but because of the fact that we end up here with the f.dr being 0, I did not notice it. So I'm going to go ahead and make a quick repair on that. So we are starting not at 300 and going up to 001, but rather at 001 and going to going to 030. So that means, gosh, so y'all see why I did things ahead of time, and yet I still have problems here. All right, so our f that we plug in there is supposed to have a y times z in it, and so that ends up hilariously still being the 3t minus 3t squared. And then when you dot that with the 0,3 -1, you get the 0 vector, or the 0 out of the dot, because they're perpendicular, and we are integrating 0, so we just get 0. it's nice when you have integrals that are super easy to do. All right. So then on y equals 0, that means that we are over here. And I guess maybe as I go along, I should do something to indicate what's gotten done and what hasn't. So on y equals 0, we're on that one there. And so we're going to start at, oh my God. Folks, apologies. That 3 is supposed to be a 2 because we're doing x, not y. Okay. On y equals 0, once again, right here, we're going from this point, the 0, 3, 0, up to the 0, 0, 1. So on that, we need to start when the t equals 0. Wow. So when the t equals 0, we need to be at 0, 3, 0. And then we need to go down to 0 there. I'm sorry. And we need the z to be going up. And when we take the derivative of that, we'll have 0, -3, 1. And then when we say something about our f vector here and plugging in, we know that we need to have yz, but okay, friends, my apologies. I thought I had an error when I didn't have an error, and consequently wasted a fair amount of time there correcting something that wasn't wrong. So let's go back to it and just run through. You've already seen part of it here, all right? Our parameterization when x is equal to 0, then we have to start at the point here that is 0, 3, 0, and go down to this point that has 0, 0, 1. So we have 3 minus 3t to get us from 3 down to 0. And then we have t to get us from 0 up to 1. The derivative of that, 0, -3, 1. And so when you do xz here, you'll have the 3 minus 3t times t, and a 0 as we had in the middle, but the x, since it was 0, it's just going to be 0. And because of the way those line up, we have a 0 being one of the coordinates no matter what. So when we dot, we get 0, and when you take the integral of 0, you get 0. Okay, I should say a definite integral of 0 always results in 0. So our vector t where y is 0 needs to have a 0 in the y coordinate. And that means that we're going along here. And that means we have to start with our z being equal to 1. It needs to go down to 0. And we need to start with our x being 0 and going up to 2. So we have the 2t there. Derivative is 2, 0, -1. And then the f vector, when you plug in the yz there, you see that y is 0, so that means the yz will be 0. You have a 0 entry, and the x being a 2t there. So when you take a dot product, you'll get a -2t, and the other parts being 0. So when you integrate that, you end up with a -1. Okay. Then when we look at the last part down here, this part that's on z equals 0, it needs to start at this point, which is 2, 0, 0. So 2 is there. And then the point it ends at is 0, 3, 0. So the x's need to go from 2 to 0. So that's why the 2 minus 2t. The y's need to go from 0 up to 3, and the z's have to stay 0 all the time. So the derivative of that gets you the negative 2, 3, 0. And so your f vector, when you plug in, your yz is going to be 3t times 0, so you get a 0. This 0 is always there, and then this is just your x coordinate. And when you dot, notice that you have zeros lining up with non-zeros, so that your dot product is just 0. And once again, when you integrate 0 across a definite interval, then you end up with 0. So that means that we have these three quantities to add up here in order to get us our line integral across the closed loop that we've got there. So we end up with -1 out of it, which shouldn't be a surprise since we got that for the surface integral already. Now, there's not a lot of purpose of doing both calculations, but I do ask you on a couple of problems to just go through the motions of doing both calculations just to see that they're getting the same thing, which is what Stokes' theorem is telling you. And then we're going to try to look at something where you actually apply Stokes' theorem. So in this example here, the surface we've got is this box that has a triangle as a base, and then it has these sides going up here. And then across the top, it's got another triangle. Now, the notion on this is that your surface has this triangle down here as a boundary, that the box is open below. Now, we could be doing one alternately that was open above or something, but just this particular one has it being open below. So the question asks us to use Stokes' theorem to calculate the flux of the curl across the surface. Okay, so we could go through and calculate the curl of this and then take 1, 2, 3, 4 different surface integrals and add them up at the end. Or we can take the vector field and just do the line integral on these 3 lines here. I tend to think that that's going to be easier. Okay, so we'll start out with, and after the previous struggle, we're going to start out with each one piece of these here. And on x equals 0, that will be the part on the y-axis. And then we've got to think about where our positive is. And it says an outward pointing normal. So that means that if you were walking along this line here, your left would be over there. So you want to go that direction, which means back here on the y-axis, we're going to go from 0, 1, 0, 1, 0 down to 0, 0, 0. So with doing that, I seem to have just randomly swapped 2 things. Okay, so this is not as big a disaster as before, because it really is just mislabeling this time, I hope. Okay, so when your y is equal to 0, so I was going to talk about when the x is equal to 0, we want to start at 0, 1, 0. And as the t increases, we'll go down to 0, 0, 0. So when you take the derivative there, you'll get 0, -1, 0. And when you plug into that yucky looking f there, you will end up with a 1 minus t, a -4, and a 0. Okay, so then you take a dot product between these two things, and fortuitously, you get the -4 and the -1 together to give you 4. So you're just integrating 4 across that interval. Super easy, right? Okay, then we're going to do y equals 0 next, because we did x equals 0 before. So when we do y equals 0, we've got a 0 here, and we're moving along here. So since we want to go from 0, 0, 0 to 0 to 1, 0, 0, we're going to have t 0, 0, and then the x's will go from 0 to 1 there. Okay. The derivative, of course, is 1, 0, 0. Plugging in that t for x and the zeros for y, you end up with t -4t. You're dotting with this 1, 0, 0, so it just pulls that t out. So you integrate t from 0 to 1, and you get 1/2. Okay. Then on x plus y equals 1, you want to start at 1, 0, 0 and go to 0, 1, 0. So 1 and then 0, 0, and then subtracting t to get it down to 0, and adding t to get it up to 1 as you go with your t's going from 0 to 1. The derivative of that is the -1, 1, 0. We plug in this stuff here to our f, and when we simplify it, it turns into 1, 1, comma, -4, and then 1 minus t times the square root of t squared plus 1. That one scared me. I was like, oh no, I'm going to have to break that into two pieces, and one of them is going to be a trig sub. But fortunately, you get a 0 being dotted by that part. And then the 1 and the 1, I'm sorry, the 1 and the -1 there, you end up with a -5 that you have to integrate from 0 to 1. Easy peasy, we get -5. And now we can say that the integral of the curl of f, I'm sorry, the surface integral, flux integral of the curl of f on that surface will be the line integral around the boundary. And then we just have to add the three pieces up. And so when we do that, we get -1/2 out of it. Now, this didn't say verify it. We don't have to do both integrals, or we don't have to do the flux integral to show that they're the same. All we're doing is applying Stokes' theorem, which says that if you want to figure out this flux integral, that you can just do the line integral instead. Okay. Take a look here at our function real quick. As we saw in an example on Green's theorem, if you don't satisfy the conditions of your theorem, you can have weird things happen. But fortunately here, the only place that we have any sort of worry at all is about having the y be equal to 0 and something changing there. But because of the fact that it's a square root of a square, we end up having things be pretty smooth in that spot as well. So in any case, we're allowed to apply Stokes' theorem. We end up with -1/2 as an answer there. All right, and this is the last one here. So the curve we've got is going to be a triangle with these vertices. And the question will be asked something in the form of calculate the circulation about the boundary, meaning to do the line integral. But the setup here, we're traversing it anti-clockwise as viewed from above. And so if you're looking down on this, you would want it to go counterclockwise or anti-clockwise there. I didn't try to get this very well drawn to scale or anything, but the notion is just to see that we've got a plane that is lifted up off the XY plane. So you don't have to do any of the stuff about breaking up into multiple little curves here. You just have to parameterize this piece of plane, okay? You can figure out the plane that we're talking about with that. For our parameterization, since we need to have the x-axis in here, then you would think about the I vector or the 1, 0, 0 vector. And then you would think about this vector here that goes out from the origin to 3, 3, 3 or 1, 1, 1. You know, either way, it would be the same direction. And you would just take the cross product of those in order to get, in order to end up with your n vector that we're coming down to here, right? So if you want a better explanation about the parameterization, you could also think about going this direction here and this direction here, where blah blah blah. I'm sorry, I'm kind of blathering on with what I'm talking about with it. But you need to be able to get up to that 3, 3, 3 there. And so I just broke it into parts that are U and V in order to do that. So when you take the G sub U and the G sub V and then take the cross product, it should turn out to be 0, negative 1, 1. Check and see whether minus Y plus Z equals 0 turns out to have both these points in it and the origin in it, and you'll find out it does. Okay. All right. Anyway, though, so this said to integrate this here, and rather than doing all of the little line integrals, we're going to take the curl of the vector field there, and you have to be able to spot that the m will be y, the n will be z, and the p will be x. And that's how I pulled this down in here. And then I took the curl of that, and I didn't write it out here because I was trying to save a little bit of space, but the curl turns out to be minus 1, minus 1, minus 1. Okay. Remember, that's not the n vector, that's the curl. Okay. So then you've got to take the curl dot ds, which really means to dot with the n vector. But this minus 1, minus 1, minus 1, when dotted with 0, minus 1, 1, you get a 0 from the first part, and you get a plus 1 and a minus 1 from the second parts. So we end up integrating 0 dv. And it really doesn't matter then what we've got it set up to do. For the surface there, we end up getting the integral to turn out to be 0. That is what you really want to happen as often as possible. You want to have to do an integral of some constant. If it's 0, great. But if it's not 0 and it's like the number 7 or something like that, then you're just doing it on a surface, and the surface is usually something that you know how to deal with. A piece of a sphere, a piece of a plane, something like that, okay? And so if you get a constant times the area of that piece of sphere or piece of plane, you can just calculate the area and multiply by 7 or 0 or whatever it happens to be. But like I say, if it's 0, better than that, because you don't have to figure out the area. So, all right, that should get y'all going and see the basic types of problems you're going to run into. One is to integrate both ways, the flux integral and the line integral, and show that you get the same thing. And then the other two sorts of problems are going to be, here is a line integral that you need to calculate, but instead of doing that, use Stokes' theorem to calculate the flux integral of the curl, and say that's what the line integral would give you. And hopefully that flux integral turns out to actually be easy. The other type is you're given calculate the flux integral of this curl, and then instead of having to parameterize your surface and do lots of extra stuff there, you instead have some line integral, which again, hopefully is relatively easy. Okay. So that's what we're looking at on these. They're tedious. You have to be very careful with your calculations. I've gone back and tried to make sure all the calculations I'm going to hand to you to work out on your own, that they're not horrifying, and that my answer is not wrong. I'll probably still make an arithmetic mistake or something, but anyway. But that should do us, right? I will see you all in class. Assuming I can find the stop button. See ya.